Welcome to Daily Papers, the podcast where we break down the latest and most interesting academic papers into something you can actually understand. Today, we're diving into a really clever paper from researchers at NVIDIA, and the topic is something that sounds like it's straight out of a school drama. How do you know if an AI is cheating on its tests?
Exactly. We rely on benchmarks and tests to tell us how good these massive AI models, or LLMs, are. Think of the AI behind things like ChatGPT. We want to know if it's good at math, or coding, or writing. But what if the model secretly saw the test questions and answers during its training?
That's a huge problem called data contamination. It's like a student getting a copy of the final exam a month before they have to take it. Their perfect score doesn't mean they're a genius, it just means they memorized the answers. It makes the whole evaluation meaningless.
And for a long time, it's been really hard to check for this. You might need access to the model's original data set, which is often a secret, or the existing methods just aren't very reliable. But this paper introduces a new method that is simple, effective, and frankly, kind of brilliant in its logic. It's called codec.
That's CODEC, which stands for Contamination Detection via Context. And the core idea is completely counterintuitive. It turns out for an AI that is cheated, giving it a hint can actually make it less confident.
Okay, that sounds weird. How does that work? If I'm taking a test and you give me a hint, I'm going to feel better about my answer, not worse.
You would if you were learning and reasoning, but a model that has just memorized the data behaves differently. Let's walk through the codec test step by step. First, you take a question from a benchmark dataset you're suspicious about. You give it to the AI, and you ask it for the answer. But crucially, you also measure its confidence in its own answer.
Okay, so you get a baseline confidence score. Let's say it's 95% confident. What's next?
Next, you ask it the exact same question again, but this time, before the question, you give it a little bit of context. You show it another, different question and answer from the very same test dataset. This is what's called in-context learning. Then, you measure its confidence on the original question again.
And this is where the magic happens. You're saying that if the model hasn't seen the test before, its confidence will probably go up. The example helps it get a feel for the style of the questions.
Precisely. But if the model has been contaminated, if it has already memorized the entire test, that extra example can actually confuse it. It disrupts the memorized pattern it was relying on. And so its confidence drops.
Wow. So a drop in confidence is the red flag for cheating. The codec score for a whole data set is just the percentage of questions where the model's confidence went down after being given a hint. A high score means it was very likely trained on that data.
Exactly right. The authors offer a few reasons why this works. One is about memorization versus generalization. Think of a pianist who has learned a song by pure muscle memory. If you play them a different part of the same song right before they're about to play it, it can completely throw them off their rhythm.
But a pianist who truly understands the music, the chords, the theory, the structure, would hear that other part and it would just get them in the right headspace. It would prime them and they'd play with more confidence.
That's a perfect analogy. The contaminated model is the rote memorizer. The uncontaminated model is the one that actually understands the music. The paper also uses a more technical analogy about the loss landscape, which is like a map of the model's knowledge.
A map of its brain, sort of.
Sort of. They say memorization creates very sharp, narrow valleys in this map. The model is like a pencil balanced perfectly on its tip in one of these valleys. The slightest nudge, like an in-context example, can knock it over, causing its confidence to plummet.
Whereas genuine knowledge is like a wide, stable plateau. A little nudge doesn't really change anything. You're still on solid ground. So the big question is, does this clever idea actually work in practice?
According to the paper, it works astonishingly well. They tested it on a bunch of different AI models where they knew for a fact what the training data was. And Kodak was able to separate the seen datasets from the unseen datasets almost perfectly.
When you look at their graphs, it's really stark. All the datasets the model was trained on get a very high Kodak score, like 90 to 100%. And all the datasets it had never seen before get a very low score, maybe 10 to 20%. The separation is crystal clear.
For the stats nerds out there, they report a dataset level AUC score of 99.9%. In simple terms, that means the test is almost flawless at telling the difference between a cheating model and an honest one. It's far better than older methods, which tend to get the two all mixed up.
And this isn't just a theoretical exercise. The researchers then used Kodak to test a wide range of modern, publicly available models on popular benchmarks, and they found some suspicious scores, not necessarily proof of deliberate cheating, but evidence that some models might have been exposed to benchmark data, inflating their performance.
So this gives us a powerful, easy-to-use tool to be AI detectives. It allows researchers and companies to hold model developers accountable and ensures that when a model claims to be state-of-the-art, its scores are based on genuine skill, not just a good memory.
It's a beautifully simple idea to solve a very complex problem. To see if an AI has memorized the test, just give it a little hint. If the hint makes it nervous, you might have a cheater on your hands.
A fantastic paper that gives us a bit more transparency into the world of AI. That's all the time we have for today.
Thanks for tuning in to Daily Papers. We'll be back next time with another deep dive into the world of research.